Welcome to my talk about PoE and the LTC4266. I'm Kyle Swenson. I work for Ericsson Software Technology, Ericsson's open source group. I'm going to talk about the motivation for both this talk and the actual work. I'm going to go over a bunch of Power over Ethernet basics, and then PoE from a system level, like how it's implemented, at least for us and probably other folks as well. I'll talk about the current upstream support in the kernel for PoE and what it looks like and how it's used. And then I'll finish off with the actual overview of the chips that I added support for, or am adding support for. So the motivation for this talk is actually Corey Mainson's talk last year at Embedded Open Source Summit in Seattle. And I noticed there was a whole bunch of questions about the hardware level details of PoE, which was surprising to me considering the group of kernel developers. So hopefully this talk will kind of be more hardware oriented, and if it's not enough, we can address that in the questions later. It's going to build a little bit on Corey's talk, but will mostly stand on its own, just FYI. And then the motivation for the work is pretty much what I do is I maintain the distribution that runs on Ericsson Enterprise Wireless Solutions routers, and I do the kernel maintenance for that, and as well as the bootloader and a couple of other things. But this is quite the challenge because we have at least 40 different products with very long product life cycles, like on the order of 10 years. And we currently have, for a variety of reasons, 6 different forks of old stable versions, mostly driven by the chipset vendor, sometimes driven by other factors, but each have a similar set of not merged and out-of-tree patches. And this comes with all the usual problems of having a old out-of-tree fork, in that it's hard to maintain. Security is always a problem. I think all these problems are very familiar to everyone here. And so ideally, I would like to run a single Linux stable version that's recent on all the chipsets all the time. That would be the ideal. A couple years ago, this was somewhat of a pipe dream, simply because the amount of effort it would have required from people was significant, and it's hard to justify that to the business. But recently, with the phenomenal chipset support being upstreamed by Lenaro and others, the DSA support from NXP and again, many others, it's becoming more and more viable to get closer to this goal. And one of those pieces is the PoE. So some basics real quick. PoE is essentially 2-part system where you have the part that sources the power and the part that consumes the power. The sourcing part is your routers, or if there's an injector or mid-span. You have different types of both PDs and PSEs, type 1 through 4, and same with the power devices. And these types mean like how much power can go across the line, which wires to use for the power. Type 1 and type 2 devices are the older ones. They're, if you see reference to like the 802.3 AF or AT, those are referring to type 1 or type 2 devices. Those go up to about 30 watts at the source. And then the more recent spec, the type 3 and 4, is also known as the BT spec. So if you see a BT PoE, that's what it's referring to as a type 3 or type 4 device, and these provide power over 4 pairs, and I'll get into what the pairs here means and how that works. There's a couple phases of PoE, which we'll get into here in a second. The detection phase, which is just ensuring that there's a PD attached on the other side, and it's not just some other NIC that you don't want to apply the 54 volts to. And then classification, how much power does the power device need or require. So powering these devices can be a little tricky, and you have to do it safely. The working voltage of recent PoE standards is like 54, 52 volts, which would not be great to apply to just your regular card, your NIC in your machine. That would not end well. Ethernet generally uses, Ethernet over copper uses differential signaling. So you have a positive and a negative. It's AC, which is convenient because we can route that through a transformer to both isolate both sides of the Ethernet wire, as well as bias that transformer and induce a DC voltage on the wire. This DC voltage is where the power is how the power transfers across the cable. The polarity is defined by which transformers are used. You have 4 transformers that you can use. Type 1 uses 2 of them. Type 3 and 4 use both of them. And then to detect that we have a PD, like a powered device actually attached on the other end of the wire, we look for a 25 kilo ohm resistance, which is important, and that resistance needs to exist at a specific voltage. It's usually implemented with just a resistor, but there's times when it may not be and may be more intelligent than that. The PSCs obviously need to accept a wider range to account for things like IR drop and that sort of thing. Moving along, the detection is the first phase of this sequence. And then once the detection is successful, we go to the classification, which is answering the question, how much power does the PD need, and what's the type of the PD, and then the PD can also determine the type of the PSE. The power requirements are determined by the current draw at this set voltage, somewhere between 14.5 and 20.5 volts. I think it's usually about 18. And the current that the PD draws, if it draws any, indicates how much power it needs. So this means that if a device, say, pulls 26 milliamps when this voltage is asserted, it needs 15 watts of power. These tables are all over the internet, and you can look it up. The more complicated part is the classification pulses and the number of these pulses. And so a type 2 PSC, for example, will do this classification sequence twice, such that the PD can know, oh, this is a type 2 PSC, and then that means both tighter electrical specifications and as well as like a software capability. The later types, type 3 and 4, do that classification pulse series multiple times. It's type 3 has 4 pulses, type 4 has 5 of them. The older devices, again, it's only up to 15 watts, which is sufficient for a lot of things, not everything. Type 2, the AT spec, means that both the tighter electrical specifications and that LLDP is supported on both sides. And they use LLDP for negotiating a power class in finer grained increments than what these 4 chunks can mean. And then the type 3 and type 4, the BT spec, sends the power over 4 pairs, whereas the last 2 types just do over 2. And then you have polarity, not problems, but you have complications with the polarity and which pairs in type 1 and type 2 the power is provided over versus the other 2, and there's a bunch of rules around that. But the type 3 and 4 use all 4 pairs, and they can enable up to 90 watts at the PSE, the sourcing side, and 71 watts at the device side. And the reason for that difference is the IR drop across the Ethernet wire, and that's usually dissipated as heat. And that's actually one of the limiting factors for the amount of power that we can put over an Ethernet cable. So moving along, once we decide we're going to power up a device, we need to do so within a certain amount of time after the end of the last classification cycle, but the PSC can choose to not power the device at all. That's important for later for things like budgeting and that sort of thing. While the device is powered, the PSC will monitor the current or the power depending on, and ensure that the PD doesn't draw too much power or doesn't draw too much power for too long. If it does, it will shut it off, and just to ensure things are safe. Additionally, the PD is required to pull some minimum amount of power all the time or in impulses, just so that the PSE knows a power device is still attached. This prevents things from like quickly unplugging a PD and plugging in a normal device and not having that normal device have some sparks fly. There is a ton more here that would take a long time to talk about, things like power demotion, auto class, and the type interoperability between the PSE and the PD. But the spec is pretty easy reading for these sections, so if you're interested, I'll let you go do that. At the system level, though, so all of this is just one PSE port so far, but almost all systems have multiple ports. Our routers have 4 usually, but many have 48 or more. It's more than one. And doing some math here, say type 4 or 4 type 2 PSE ports is about 120 watts maximum that you'd need to design your power supply for, which is a really tough sell when your router without PoE takes about 12 watts. And so having to have an order of magnitude larger power supply is expensive and not really realistic, especially because the vast majority of deployments aren't going to use anywhere near this amount of power, even if they do have 4 type 2 PDs attached. So if we say that we can't provide the maximum power to all the ports all at the same time, how do we decide which ports get power, which ones don't? Well, like all of these sort of hard questions, we let the user decide. They can decide by setting a port priority that's implicit by the port number. There's a variety of ways to implement the priority itself. The more interesting thing isn't the priority mechanism, it's what you use to decide the ports, what ports stay powered and which ones don't, and how you do that budgeting accounting, if you will. So there's 2 conceptually distinct ways that are implemented in the kernel as of like last week. Last week on NetNext. The first is static, which is where you use the maximum class allocation for that PD, and then you subtract that value out of the system level power budget that you have on that platform. This is good because it doesn't change, and a operator that's plugging in these devices on site can know if some of them power, some of them don't, and it'll always be the same. But similar to the system level, a 30 watt PD is very unlikely to constantly be pulling 30 watts, and it's pretty rare. So you're wasting quite a bit of your power budget, in a sense, with the static budgeting. So to solve that problem, you could use dynamic, which is using the currently active amount of power for each PD. And so if you say you have 4 type 2 devices pulling 30 watts or so, you could power, or less than 30 watts, you could power a 5th or 6th device if that's total is currently under the total system power budget. This is good for efficiency, but it will make your lower priority devices possibly be turning on and off somewhat quickly. And when it turns on and off is dependent on other devices attached to the PSE. And so that could cause some complication. But both are appropriate depending on the use case, depending on what the system designer needs or wants. So it's the choice, I guess, is yours, and both are supported, soon to be supported, but none of that's my work. That's all Corey's. And this, I've kind of alluded to this. The PoE framework is relatively recent. It is very recent, actually, and added last year. And again, he talked about it. There's a link to it in the slides if you're interested. He added support for two chipsets that we support. There's a third, the LTC4266 that we have in our platforms. And he just got this prioritization and budgeting merged. And then, very interestingly, I found on the mailing list a new PSE chipset I had not heard about, the Skyworks chipset, which is super cool. It was a pleasant surprise to see that. And then mine's posted as RFC at the moment. But all this goes to show is that there is significant interest in PoE in the kernel, and it was sort of pent up in the sense that all of a sudden, as soon as the framework was there, all these drivers started appearing out of the wild, which is really cool to me. The framework is pretty dead simple. It's similar to most of the other driver frameworks in the kernel. You have a struct PSE controller that describes a particular chipset. You have some ops that the core uses to call in and get status, that sort of thing. The user space API is via netlink. So you can use ethtool, Pyte, NL, variety of things. It's netlink, so it's great. Yeah, the ethtool pieces have just, I think they're still posted. I don't think they've been merged quite yet, but they'll be merged soon. So maybe in next kernel release or so, you'll be able to use this if you have any of this hardware. And then so adding the support for the last PSE chipset on our routers is somewhat straightforward. It's an older chipset. It only does type 2. And it's hard to tell how widespread it is in the industry, but we'll see how useful it is later after it's merged. There's a variety of operating modes, automatic, and this is true of many PSE chipsets as well. You'll have an automatic mode where there's no software control, no software involvement. It'll just power the devices or not, or no, always power the devices. So you need to make your system level power budget be able to power all the possible devices. There's a manual mode on this chip, which allows you to apply the 54 volts on the wire without doing any detection or classification. If you just want to see what happens, I don't really recommend it. The useful mode in most of these chips is the semi-automatic mode, where it will detect and classify constantly, and then the software control can decide if it wants to power or not the device. The sort of tricky thing, at least to me, is the current limiting support in the chip. So it doesn't limit by power, it limits by current. And this complicates the power budgeting algorithm and stuff in the framework. And I don't have a great solution in the RFC series, that's why it's RFC. So if you're interested in checking it out and you're like, oh, well, obviously you should do this, let me know, because that'd be helpful. I guess with that, I'm done, which was super quick, sorry. Anyway, special thanks to, again, Corey and Oleski, the two maintainers for this area. They're great to work with. You should say hi if you see them. I don't think they're here, but in Amsterdam or something. Anyway, questions, comments? Oh.
Thanks. I saw your version, or not version 1, but RFC in lore, and was wondering how version 2 is coming along, because there's a lot of comments, and I was also curious about your solution to some of them. So
Yeah, so I've not checked it recently. I've been kind of freaking out about this presentation.
That's so fair.
The DT binding stuff has always been super hard for me, and I don't know. But I'll address all those, and although even though past check patch and all that stuff, it's still Christoph had some problems with it, but that's okay. I'll fix all those, and that'll be fine. The current limiting stuff, I don't know if that was common. Is there anything in particular you were referring to, like any problems that you can remember?
I think I'll have to look back at it and maybe point to some lines.
Yeah, okay.
I remember.
Well, so I guess to answer your question, how's it coming along? It's gonna soon, probably. No, it definitely will. I do care a lot about this, and it will happen. It's just a matter of time.
Okay, cool. I just had talked to Corey about when he wanted to support the TI PoE part. So now it's nice to see
Yeah.
it's all coming together.
Yeah, yeah. It was really cool when I went to his talk and was like, hey, we should talk about this. This is awesome. How's the power budgeting going? He's like, it's not really planned. I'm like, let's do it, dude. So it is cool.
No, it's really good work. Thank you.
Yep.